Hello friends, I am Professor DGT. I am going to teach you now decoding gates. Previously you have studied about asynchronous counter. In an asynchronous ripple counter, the output of the counter can be connected to the gate and the different state can be decoded. You know that the ripple counter, we have studied two types of the ripple counter. One is a modulus of 8 counter, another one is a modulus of 16 counter. Now, what is the modulus of the counter? The number of discrete states through which counter can progress, and then after it will repeat into that sequence. That is called modulus of the counter. In a modulus of the counter, there are different states. If you want to decode a particular state every time when the cycle is going to be repeat, then you are going to utilize decoding gates. Decoding gates can be anything, either AND gate, OR gate, NAND gate, NOR gate, etc. And output of the gate is going to be either low or high when that particular state of the counter is going to be contained. So the decoding gates can be connected to the output of the counter in such a way that the output of the gate will be either high or low only when the counter contains or equal to a given state. For instance, the decoding gate connected to 3-bit ripple counter in figure 10.6a will decode the state 7, that is CBA is equal to 1 condition. So this is the state number 7 which we want to decode. How the gate output should be connected, how the counter flip-flop output should be connected to the input of the gate. The output of the counter A is 1. Output of the counter B is going to be 1, and output of the counter C is going to be 1. That is supposed to be connected to the input of the gate, and the waveform appearing at the output of the gate is labeled 7. The Boolean expression for this gate can be written as 7 is equal to CBA. The other 7 states of the counter can be decoded in a similar fashion. You have to locate the which state you want to decode from the truth table, and corresponding to that truth table state, you have to find out what is the Boolean expression, and you have to connect the combination of that Boolean expression to the input of the AND gate such that when that particular state of the contain of the counter is going to be there, then that state is going to be decoded. It is only necessary to examine the truth table for the counter, and then the proper Boolean expression for each gate can be written. For instance, to decode the state 5, the truth table reveals that C, B and A is equal to 101. That is the truth table. Is the unique state. For the gate output to be high during this time, we must use C, B bar and A at the gate inputs from the counter. Notice carefully that if B is equal to 0, B bar is going to be 1. So all the 3 inputs of the AND gate is going to be high, and when this particular state 101 is occur, then output of the gate is going to be high. That means it will provide 1 pulse. The correct Boolean expression is then phi is equal to C B bar A, and the desired gate is that given in figure 10.6a. The waveform for the state phi is labeled as SID. Now you can see this figure. This is a 3-bit ripple counter. 3 JK flip-flops are connected in cascade mode or in a series mode. So it is known as a ripple counter, serial counter, or 3-bit asynchronous counter. All J and K of all 3 flip-flops are connected with the VCC, and hence it is working in toggle mode conditions. Clock is applied to the first flip-flop A, which is supposed to be LSV. Output of A is connected to the flip-flop B, and output of the C is going to be B is connected to the flip-flop C, and hence the output goes through the particle to particle. Here you can consider from flip-flop to flip-flop, and hence it is known as the ripple counter. Now, suppose you want to decode the state 7. So, here you have utilized the decoding gate AND gate. The output of C is equal to 1, output of the B is equal to 1, and output of A is equal to 1. Then and then only output of this gate is going to be high. That way, it is going to be decoding the state number 7. The same thing you can see in the waveform also here. This is the first one, the clock waveforms. Negative edge of the clock waveform, the flip-flop is going to be triggered, and it will result a toggle. That means output is going to be complemented. So, every negative edge of the clock pulse, the flip-flop A is going to be toggled. You can see that here, the negative edge of the clock pulse A is going to be changing the state. Again at the negative edge of this clock pulse, flip-flop A is changing the state. Again at the negative edge, the flip-flop A is changing the state. So, every negative transition of the clock pulse, A is going to be toggled. Similarly, output of A acts as a clock input for the B. So, B is also going to be toggled with negative edge of output of A every time. And similar things for the waveform C. That C is also going to be toggled when output of B acts as a clock input for the flip-flop C, and output of the B when make a transition from high to low, the flip-flop C is going to be toggled. And that way, this is the waveform drawn for up counting of 3-bit ripple counter. Now, you can see that here. Then after, there is a waveform for the state number 7. When you can see here that A is equal to high, B is equal to high, and this is going to be high, C is equal to high, then and then only output of the gate is going to be high. That means decoding gate 7 will produce output pulse when A, B, C is going to be high. Suppose you want to decode the state number 5. Then A is equal to 1, B is equal to 0. That means B bar of the flip-flop should be connected to the input of AND gate instead of B. So, B bar is going to be high and the state number 5 is going to be decoded. You can see here. When A is equal to high, B is low, but B bar is going to be high and C is also high. At that time, the pulse is going to be resulted output of the AND gate, and that way the state 5 is going to be resulted. So, what is the input of the gate which is connected? A, B bar and C. These are the input to the decoding gate connected. So, it will decode the state number 5. Similarly, you can decode any other state also in a similar manner. That means you have to look into the truth table, you have to find out the Boolean expression for that, and that according to that Boolean expression, you have to connect the input of the AND decoding gates, and that state is going to be resulted. All 8 gates necessary to decode the 8th state of the 3-bit ripple counter is shown in this figure. The gate output are shown in figure 7b. This decoded waveform are a series of positive pulses that occur in strict time sequence and are very useful as a control signal throughout the digital system. So, what is the use of the decoding gates? I'll show you. But before that, you see that if we are having a 3-bit ripple counter, number of states is going to be 8. Modulus of this 3-bit ripple counter is going to be 8. That means there are number of discrete states is from 0 to 7. To decode a 0 to 7, how the input of the gate are going to be connected? That you can see here for different decoding gates. A bar, B bar, C bar is connected for the decoding state 0. A, B bar and C bar is connected to decode the state number 1. A bar, B, C bar is connected to decode the state number 2. And to decode the state number 7, A, B, C is connected to the gate. So, these are all 8 gates which is required to decode the different states. Now, you can see that if the counter is operating in count up mode, that means it is operating from 0 to 7, then the content of the counter is going to be advancing from 0, 1, 2, 3 like that way. And if you are utilizing all 8 gates to decode the different states. The states which are going to be decoded is from 0, 1, 2 up to 7. That you can see that. And the waveform which is shown here. So when A is equal to 0, B is equal to 0, C is equal to 0, then the decoding gate 0 and gate 0 output is going to be high. And for the remaining period, it is going to be low. Again, you can see that here it is that condition is going to be happen when the sequence is going to be repeat. A is equal to 0, B is equal to 0, and C is equal to 0. Again, the output of decoding gate 0 is going to be high, and you can say another pulse is going to be resulting. Similar things for different states. Again, if you want to decode state 1, then what is the output? CB, A bar, C bar, B bar, and A. That should be connected to the gate. And that way, when this condition is going to be there, C is equal to 0, B is equal to 0, and A is equal to 1, the state 1 is going to be decoded. So, just as soon as output of 0 is going to be low, at that time, the output of gate 1 is going to be high, and it will provide one pulse. Similarly, state number 2 is also decoded, state number 3 is decoded, state number 4 is decoded, state number 5 is decoded, state number 6 is decoded, state number 7 is decoded, when ABC is going to be high. Again, when state number 0 is going to be there, again you can see that sequence is going to be repeating here. So, these waveforms which are going to be obtained here, these pulses are strictly occurring in a time sequence. You can see that when the 0 state is going to be completed, 1 state is going to be started, 1 state is going to be completed, 2 state is going to be started. That means strictly they are occurring in time sequence. And that means because of they are strictly occurring in time sequence, they can utilize as a control signal in any digital system or in a microprocessor where you are using a control bus. For control bus, read signal, write signal, such kind of signals you are using in a sequential form. There you can utilize this kind of different time sequence waveform is going to be utilized. If we consider state 0 as the first event, then state 1 will be the second event, state 2 will be the third event, and so on up to the state 7. Clearly, the counter is counting upward in decimal notation from 0 to 7, and then beginning over again at 0. If the counter is operating in countdown mode, the decoding waveform will appear as in the figure 10.7c. So, if the counter is operating countdown mode, the waveforms is going to be appearing like this way. That you can say that when 0 state is going to be there, the decoding gate is going to be the same. So, A is equal to 0, B is equal to 0, C is equal to 0. This is the waveform for countdown mode. So, 0, 0, 0 conditions, then 1, 1, 1 conditions, that means state number 7, then 1, 1, 0, that is state number 6, then 1, 0, 1, that is state number 5. So, content of the counter is decremented with every negative edge of the clock pulse. So, it is operating in countdown mode. And because it is operating in a countdown mode, and the same way the decoding gates are going to be connected, you will see that waveform are going to be resulted in this fashion. And you can utilize the same way this waveform also in a strictly time sequence, and hence can be utilized for control signals in any digital system. In this case, if the state 0 is considered to be the first event, then state 7 is the second event, state 6 will be the third event, and so on down to the state 1. Clearly, the counter is counting downward in decimal notation from 7 to 0, and then beginning again at 7. If these 8 gates are connected to up-down counter shown in a figure 10.5, the decoded waveforms will appear exactly as shown in figure 10.7b. That means when it is operating in up mode, it will be 10.7a, and when it is operating in down mode, it is 10.7b. The clock and each flip-flop output are redrawn in figure 10.9, and the propagation delay time of each flip-flop is taken into account. Now, we are looking for something else. If we are having this kind of decoding waveforms, but if we consider that propagation delay time of each flip-flop is also considered to draw this waveform, then what will happen? That kind of waveform is going to be shown in a next figure, that is 10.7. You will see that because of the different propagation delay time from different flip-flops, there is a glitches, or which is known as the unwanted signal, is going to be occur. Notice carefully that clock is applied to the flip-flop A, and the output of flip-flop A waveform is going to be delayed by propagation delay time Tp from the negative edge of the clock pulse. That means it is not occurring exactly at the same time when the negative edge of the clock pulse is going to be there, but it is delayed by Tp of negative edge of the clock pulse. For reference purpose, complement of A bar is also shown because we are going to decode the state number 6, which is CB A bar 110, and hence the waveform of A bar is required. So we are drawing here the waveform of complement of A, that is A bar is also drawn in the figure. So we can utilize to find out the decoding gates output state number 6. Since A acts as a trigger for the B, again output of B is not going to be occur when the negative edge of the A will occur immediately, but it will be delayed by propagation delay time of Tp of flip-flop B. And similarly, the C waveform is also delayed by propagation delay time after the negative edge of the B waveforms, which you can see here. This is the timeline, and in the timeline these are the negative edge of each clock pulse. That means when it is changing from high to low, it is said to be the negative edge. Output of A is occurring, but output of A is not occurring exactly at the same moment when the negative edge occurs of the clock waveform, but it is delayed by Tp, propagation delay time. Output of A is also redrawn here, but A bar is not delayed because A and A bar are complement to each other. That means A bar is just mirror image of waveform A will be there. So here the waveform A bar is drawn, which is supposed to be the mirror image of waveform A. Now waveform B is drawn here. You can see that the waveform B is going to be occur, or it is going to be complemented when output of A is going to be triggering the flip-flop B. But the waveform B is not going to be occur at the same moment. It is also delayed by propagation delay time Tp. Similar things is going to be happen for the flip-flop C. See here, this is the negative edge of the flip-flop B, but output of C is not going to be occurring at the same moment. It is delayed this much amount of propagation delay time. So now, what is happening now? If you see that you are decoding the state number 6, that means when the output of flip-flop C, B and A bar is going to be high, the pulse is going to be generated. That is state number 6. Output of the C is going to be high, output of the B is going to be high, output of A bar is going to be high, then the pulse width is going to be generated. The same kind of condition is going to be resulted between the time period A and B, where C is also going to be high, output of B is also going to be high, and output of A bar is also going to be high here. So for this time period, all the three inputs C, B bar, B and A bar is going to be high. So the clock output of the AND gate will generate small pulses, and this pulse duration is very short and it is unwanted. So it is known as a glitch. Why this is going to be happening now? Let us say at time when the output of the pulse, when it is changing state from 7 to 0, output of A is making a transition from high to low, right? But output is not going to be making a transition at when the clock makes a transition from high to low. But it is because it's the propagation delay time, the flip-flop output is changing high to low at the instead of time A, instead of this time. And because of this, there is a brief instant of time when A bar is going to be high, B bar is going to be high, and C bar is going to be high. So B is not going to be becomes low prior to A bar becomes high, and hence there is a negative edge is going to be occur. At first glance, this delay or this glitch, which is called unwanted signal, is not creating much problem because the duration of this glitch pulse is very, very small. Even sometimes it may not be appear on the oscilloscope. But because the TTL is very fast and it can respond to even the smallest amount of these glitches. And because of that, you can see that even we cannot see on the oscilloscope, but it will create a false triggering into the further digital system. And hence, these glitches should be removed. And there are two ways these glitches can be removed. Consider, for instance, the gate used to decode the state 6. The proper Boolean expression is CB A bar. So, in figure 10.9, the correct output waveform gate is high only when C is equal to 1, B is equal to 1, and A bar is equal to 1. But look at the glitch that occurs when the counter progresses from the state number 7 to the state number 0 on the timeline. A goes low, A bar goes high at point A because of the flip-flop delay time. However, B does not go low until the point B on the timeline. Thus, between the points A and B on the timeline, we have a condition C is equal to 1, B is equal to 1, and A bar is equal to 1. Therefore, the gate output is high and we have a glitch. Look at the waveform 6C is equal to CB A bar. Depending on how the decoder gates outputs are used, the glitches or this which is known as unwanted pulse or unwanted signal may or may not create a problems. Admittedly, the glitches are only a few nanoseconds wide and may even be very difficult to observe an oscilloscope, but TTL is very fast and TTL circuits will respond to even smallest appearing glitches, usually when you least expect it and always at unwanted time. Therefore, you must beware to avoid this condition. There is two solutions to remove this glitch problems. One method involves stopping the gate. What is this stopping of the gate? That means instead of using a 3-input AND gate for decoding state, we can utilize 4-input AND gate to decode a particular state, and the 4th input is utilized as a clock itself. So, when all 4 input is going to be high, that means when the state number 7 to state number 0 makes a transition, at that time you can see that between the time periods A and B, clock is low, and because the clock is going to be low, the glitch is already removed. In actual waveforms, the output of the gate, the glitch will not be appear. This way, glitch can be removed. There is another way also glitch can be removed. So, in place of the asynchronous counter, if we utilize the synchronous counter, then also your waveforms are going to be glitch free. This synchronous counter, which we are going to study in next section, here it is we are using the stopping the gates, and that way one more input decoding gate is supposed to be utilized and clock is utilized. But here there is one thing you have to notice, that width of the pulse 6 is equal to width of the clock pulse is going to be there, because the pulse width is going to be decreased. But that has nothing to matter, because that pulse width is enough to trigger a next circuit. So the pulse width of the decoding gate of the 6 is going to be the pulse width of clock waveforms. Thank you, dear.